You're listening to a Pop House Network podcast for developers by developers. Welcome to Java Pop House episode 105. AI. Hey everyone. My name is Freddy Guime. I am one of the co-hosts of the Pop House podcast. I am a distinguished principal engineer at Expedia, author, speaker, Seattle Java User Group co-organizer, and I'm here with my partner in crime.
Hey everybody, Bob Paulin, software engineer at Datavolo, Apache Software Foundation member, Java champion, and CJUG board chair.
All right, and before we dive into this super cool episode of Pop House, I wanted to thank our sponsor, Datadog. Today's show is sponsored by Datadog, a monitoring and analytics platform that integrates with over 450 technologies, including AWS services, Docker, and Kubernetes. Datadog's platform brings together metrics, traces, and logs in one place, so you can get full visibility into your environment and improve your application performance. With machine learning-based alerts, customizable dashboards, and distributed tracing, Datadog makes it easy to unify disparate data sources so you can troubleshoot faster. Start your free Datadog trial today. Listeners of this podcast will receive a free t-shirt once you install the agent and create one dashboard. Visit javapophouse.com/Datadog to get started. And again, that URL is javapophouse.com/Datadog. All right. So, I wanted to dive into this particular episode because this is fun. Like it's essentially AI is eating the world, and so much that Bob actually went out of. He's working now on AI. That's how big of an influence it is, right? And sometimes we're kind of like running, and we never get a chance to like slow down and understand what's really happening behind the scenes, right? And like I don't know what your thought process was, Bob, but once I learned like what was really like what is this big ChatGPT 4.0 was doing, I was like, oh crap, that's it.
Yeah, I mean, so it's funny. I'd say I was doing AI before it was cool, but AI seems to go in and out. And it has actually been doing that for decades, right? So, I mean, back in the 80s, they thought AI was close. It was going to achieve, artificial general intelligence. Little did they know there's a lot of blockers that come up. So, I mean, it's one of those things that seems to grow in fits. But now it's like we're at the point where there's a lot of stuff you can do that is really useful and requires very little effort on the part of the user. But the funny thing is, you've got a screen capture of a neuron up here and all of that. Those were concepts that were around, in the late 80s or early 90s when you started talking about neural nets and backpropagation and some of the research that was going on. And really all it's been is a lot of the things that we're using now, they're scaled up versions because now computationally we can do things that we couldn't do before. We've learned a little bit about what does and doesn't work as far as training, as far as, how we can build systems that can run these things in parallel. And now we're at, a point in time where, yes, I joined an AI startup because there's just a lot of things happening right now and a lot of growth. And it's really a fun place to be around. But yeah, conceptually, the things we're going to talk about today are a lot of the things that have been around actually for a while. But, we're going to talk about them and talk about how they relate back to, the general Java programmer that's probably being thrown into, hey, I now need to learn AI stuff to figure out how I can do my job better or integrate these things into the things that are already serving our customers and making sure that I have a job for the next 10 years or so.
Yeah, no, yeah, after this episode, you can throw words like LLM, RAG, and people will be just jumping to hire you, right?
Oh yeah, absolutely.
So let's go back in time, right? Look, what AI or large language models are like, they are a subset of AI, and I'm gonna shamelessly steal, well, we attribute the actual article, but and we'll put it in here, is like, this is kind of like where it really stands, right? Like, AI is the kind of like the field in our in like the field that in computer science, but elements is kind of like a little bit, it's really embedded into machine learning and deep learning, and a lot of these kind of like are underpinned by the concept of neural networks. Now we always hear, and like Bob said, like the breakthrough that happened was that we can make very very large neural networks today, right? Like before, we were kind of like limited um on how big can we actually train these neural networks. One of like the breakthroughs that has happened is that we can actually create very big neural networks, right? And to understand what neural networks are is like, we start with neuron, right? Like, and the funny part is, for those who actually has studied um biology, right? Like the way that the brain works, right? It's like, and then not like, I'm gonna butcher it, but and the very principle of
Oh,
it is like, they are like this little neurons that are floating around, and sometimes they get stimulated and shot electricity to another neuron, which in turn kind of like has a decision. It's like, oh, maybe I want to like essentially fire myself up, or I'm just gonna like let it be in, and I'm not gonna fire a pulse downstream on the other neurons, right? So somebody decided to, let's just replicate that in code, and kind of decided to create this idea of neurons within the code. And the way this works is, here we have a picture of a neuron by V7 Labs, where there is stimuli, and the stimuli could be just, essentially is usually numbers, like, a number can be from, a double number, or 0 to 1, or all these other things. And essentially, the stimuli, you kind of like add them up together, and there is a point of essentially probability where, ooh, the stimuli got like big enough that now I'm gonna fire up, and essentially fire up the active, what they call the activation function, right? So the idea is that, you might get like values coming through like 0.1, 0.5, 0.8, and suddenly the adding of this makes it as like, oh yeah, then I should fire a new value at 0.3 downstream. Now, there's a couple other things here, like there is the first one is like, these WKs are like what is called weights. So the stimulus might be like 500, and there's a weight to it to kind of like amplify or reduce that value. And there's also a bias, which is kind of like something you insert for, as a bias for that neuron to fire more often or less often, depending of the behavior you're training that neural network to do. And like, so individually this seems like something super simple, like in terms of the thing, it's like, get some inputs, add them together. If it passes a threshold value, I create an output that is also a number. And if you think about it, say that you put some neurons behind this as well, and the output now becomes the input of another neuron, and that is really essentially what we call a neural network. It's essentially a bunch of these little things. They have this kind of like biases. They have this kind of like weights uh, that will take some input and then essentially emit the output, right? And as part of it, the input is usually something numerical. It's not like an image, but the interesting crazy part is, for example, if you essentially make an image to be just the RGB components of it, and then the RGB components are the inputs to a neural network, then you can start training a neural network to say like, oh, there's a cat in this picture, even though it cannot actually see. But because the neural network is trained on a particular kind of set of data, then it can actually then learn how to see the quote unquote things by just using the RGB values.
right. And let's take a step back, because I mean, you mentioned training, you mentioned input output. So I mean, the screen capture you have here is just a small piece of what would go into a live neural network that can actually do something realistic. So what you're seeing is weights being attached and then an activation function deciding if it's going to fire, and then output generating. That output is going off into many different layers of the neural network. And when you're talking about, you know, current day LLMs, like say ChatGPT-4, they have 1.7 trillion parameters going into them. So, I mean, this document has an M on it, 1 and 2, but imagine that going to 1 trillion. And those are the numbers of inputs that are going into these models, and then through multiple layers in order to come to an output where, you're being able to generate something that sounds almost human sometimes when you're using chat completion with these LLMs. So the scale of this goes up very high, and in order to get to the point where these networks that are set up, they have different architectures to them. You have different sets of parameters being sent to different types of networks, and you're training these networks to respond to those inputs in a way that makes sense. Takes a long training process and a lot of example material. So, when you're talking about training, and you're getting input and you're trying to create output, a lot of times what you're starting with is, here is some input that I'm going to send you. This is some output that I would expect. So you would have both a sample as well as a key to that sample. And you would have many, many examples of that. And you would feed the input data in, and you may not get what you expect, but you say, well, this is the output that I do expect. So I'm going to send something back through the network to tweak the weights, to tweak, how I bias different parts of the network, to hopefully tune that result to get closer to what I expect the next run through. And that's essentially what training is, right? So I come up with a lot of different inputs that trigger all of these different parameters. I know what the output's supposed to be, so I can calculate how close the output is, because usually the output is itself a vector of some sorts. It's a bunch of numbers that signal different things of what that output might mean. Whether, in the case of a vision model, they could be bounding boxes that were detected, or a classification. So, when you get into a bucket to say, oh, this is a dog versus this is a cat versus this is a human being, and this is where they're located, those are all different output parameters in these models that you're trying to train to say, if I give you this input and I had somebody draw coordinates on an image of where the bounding box is and what the thing is that's in that image, this is what I expect you to output. Oh, you didn't do that. Okay, but you were kind of close. You detected a cat, but it was off. All right, so I'm going to go back through and I'm going to change the weights to try to see if we can get closer to the bounding box that you were off on. But please don't mess up. You got it right. It was a cat. So these are all different examples of how you use these network architectures to get the results you want. And you honestly, you do this a lot. Like the training of these models is computationally very, very expensive and require a large number of examples to do anything that is halfway interesting. So, part of it, it's not only part of the computation being available, it's also of the amount of training data that's available, that's often been annotated by human beings that are looking at these things with their eyes and saying what the results should be in order to train, an automated model to do a lot of this work.
Right. And this is like a picture of what it looks like, right? Like, you have the input layer. The hidden layers are essentially the intermediate layers of the neural network, and we know that these guys are neurons. And then the output layer, right? And here you say, like it's saying, like, oh, there's a difference of what I wanted you to do, and kind of like then what is called, like, it back propagates throughout the networks, doing the adjustments of the little biases and the little weights that each neuron has, right? And And that's really the trick, right? Once you start doing this at a scale, then you kind of then um, are able to produce interesting results, right? And one of the things that happens, for example, is that um, you know, uh, you can get, essentially do exactly the same exercise and create a neural network that is based on text, right? And once you train it in a lot of text, and I think like that was the thing that ChatGPT 3.5 essentially trained it on, most of the internet text that exists out there. You can start asking the neural network, hey, tell me what is the next word that should come up after this, right? And it kind of, you this is the input that goes into the neural network, and then the neural network, then the output is the probability of the word being the right word to choose, right? And this is the fun part, is that if it then once it decides that this is the word, then it takes that new sentence and feeds it back again into the neural network to predict what is the next word that is going to come out. Uh, like it's kind of like if you ever use an LLM, you kind of see this stutter that it comes with it, right? Like when it starts producing words, but it's not like it just shoves all the text in. What it's doing is like essentially it's predicting what the next word should be, then taking that and feeding it again onto the neural network to predict what the next or n+1 word should be, then takes that, feeds it again, and then it predicts what the n+2 word should be. And really, that is the whole trick. Like, it really is a neural network that has been trained on tons of text and that is trying to do the prediction of the next word that's going to come out. So essentially, with that, and I think this is kind of like the interesting part where I think GPT 3.5 has like a corpus of text, and for example, there is actually like the different LLMs will be trained on different data sets. I know, for example, Phi 3, which is the one from Microsoft, is trained on just scholastic data, or not scholastic, scholarly data. So essentially just like abstracts, like scientific papers and stuff like that. So it's very stiff on its responses, or the responses come like if a teacher talking to you, right? Uh, the LLMs that are GPT 3.5, 4.0, they are trained on more of like regular data, including like I think a lot of like internet, websites, forums, and stuff like that. So it has, it can achieve a more casual tone, right? um I think the next component to kind of start understanding this is I, like, do you think we should, and I ask about, do you think we should go to embeddings, or do you think or am I missing something else before we move on?
Well, I mean, the embeddings is kind of a natural continuation, right? So, with when you have an LLM and you're basically trying to, um, so we've talked about inputs, we've talked about outputs, right? So, in general, those outputs signify certain things, right? So when you get a signal on one of those outputs, it's generally classifying it to some specific thing. It could be a characteristic, it could be a sentiment of the text. It's something that the LLM or the system is going to use to say something about what that input means. Um, so one thing that Freddie mentioned a bit is that these neural networks, they often take a little bit to go through all of that processing in order to generate, either when you ask it, say, here's some text, summarize it for me, or you're going to say, here is some text. Let's just put it through and see what kind of characteristics we would classify that with this LLM, which is what you would call an embedding. So if I feed text in and I say here, create an embedding off of it, you're taking the outputs of that model with that text and you're creating a large string, or well, not a large string, but a large array of numbers, also a vector of what that result is. Now that vector, I can feed other text in, and it's going to get classified using um, the same output nodes that that first vector was. So now I actually have two vectors that I can use to do comparisons with on those strings of text. So I might be looking to say, well, how similar are these strings of text across the list of characteristics that this model is measuring? And, you know, when you're talking about vectors, mathematically, usually you're kind of thinking about a distance function or error so that you can take those numbers and figure out, okay, now if I were going to say this is an n-dimensional vector, which is really just a string of numbers, and I want to calculate the error about how far off they are from each other, there's formulas that I can take those two numbers and compute, you know, a distance between those vectors. And the bigger the distance, the more dissimilar they are. The closer the distance, the more similar they are. Hypothetically, you know, if you have a model and you bucket different characteristics, let's say, you know, if you're bucketing whether they're talking about characters, whether there's a dog or a person or a cat, and each one of those has a signal, an output signal, and you have another piece of text that is maybe just talking about a dog, well, they're going to be very similar on one aspect of that vector, but the other two, there may be no signal, or maybe, you know, there's going to be a distance away because it's not talking about a person or a cat. So if you have an article that's maybe talking about all three of those things, and you have another one that's talking about all three of those things, they should all signal fairly strongly on those. So the distance between those are not going to be very large, and those are going to be matches as far as similarity. So the idea of taking text, running them through the LLMs, and then storing the result in a way that, you know, I can bring those results together if I'm trying to find things that are similar and then get back to the text. I mean, we're starting to get a little bit into RAG now, but it all kind of starts with being able to take text, break them down into vectors, and then being able to make find similar things to bring in about those vectors in order to do more work with them, essentially.
Yeah, no, and this is and it's fun because like you know, and showing my age. When I went to college, there was not a computer science department. It was the computer science and applied mathematics. And that's how the old school, like, you know, like when computer science was just coming up, it was like, oh, this is a branch of mathematics more than anything else. Now I think it's most colleges would just do computer science, right? And one of the things that happen in there is that, you know, and this is kind of like the classes that you say like, oh, I'm never gonna use multidimensional algebra ever in my life.
Well,
If you like math at the time, I have good news for you. If you hated it, well, it's still good news, right? But that is kind of like what we said, right? And this is kind of like a three-dimensional vector, but the interesting part is that it's not really just three dimensions, right? Like that is the three dimensions is for us to help us visualize, but in reality, this is really like what they call hyperplanar or multidimensional vectors, right? Like it's definitely more than three. Usually it's 100 or 500 or 1,000 dimensions, right?
or a lot more.
Yeah. If you try to imagine it, your brain kind of like just like locks up, right? Um, but yeah, but it's kind of funny because like even if in this hyperplanar geometry, vectors are still this like the math that is like how close are these two vectors? What is the angle between them? It's still the same math if it's one dimension or a million dimensions. So the fun part is that because of that, we can see how similar these vectors are in all these multidimensional ways. And really, this is also the linchpin of a lot of searches, right? Like when you're thinking about just your regular, not even like LLM searches, but just your regular Google search or your regular like document search, they kind of do the same thing. Like they try to qualify documents on vectors, or they try to create vector spaces, and then they try to figure out, like if you're searching for a particular word, then it tries to see, oh, that word is similar to these other words. Therefore, maybe we can find these other words in this document. This document has more similar to the things that you were searching for. So,
Yeah. I mean, there's a little bit of an evolution again when you start talking about, classic search where you're taking keywords and you're stemming them, where walk and walking actually stem to the same word, so that when you do a keyword vector, so you can have these very large sparse vectors where it's like, did this keyword show up out of all of these keywords in this corpus? And I can find documents that contain those keywords and rank them based on, which ones are the most infrequent ones, because the theory is an infrequent term appearing in two documents is a stronger signal that they're similar than common terms, which is a Zipf distribution is what they call that, is where the very common terms kind of fall off because they don't add a lot of weight.
like
But
the
you end up with these very large sparse vectors of all of the words, the stemmed and processed words that you would have in a corpus. And that's a lot of how old school search happened. But now, instead of using the words as buckets, you're using the output of the LLM as buckets,
Mhm.
which can be a little bit smaller because you're not including every single word that appears in the corpus. Now, you're just using however large those output dimensions of that embedding model is as the number of characteristics. And those are fixed numbers. So everything that you generate is going to have the same number of buckets, and those buckets are going to mean the same thing. So those vectors, you're going to be able to calculate similarity off of that. And I don't know if that's where you're going with it with
Yeah,
this slide, Freddie, is you're showing that if you have a vector that is talking about verb tense, and it's been trained to recognize past tense versus present tense, it's
mhm,
going to have present tense verbs clustered together and
mhm.
past tense verbs clustered together, where there's going to be very little distance in the plane between them. Now you also are showing a little bit more of also walked and walked. Now in my head, that is probably another bucket in your vector of whether walk and walked are that third dimension, maybe another
Right,
dimension
right.
vector, to say, oh, it's not just the word verb tense, that is the actual verb that
Action.
is
Yeah.
associated, the action that's okay. So the verb is close, but the tense is far off. So there is a distance between those. Swam
Mhm.
and walked. Okay, the actual verb is different, but the tense is the same. So you have them on a similar plane.
Yep. Yeah. And what that brings a little bit is this idea that sometimes when you start talking about LLMs, suddenly a vector database starts showing up, right? And you're like, okay, I have an LLM, and suddenly you're trying to figure out, oh yeah, but you also need to stand up a vector database, and and you're like we're trying to figure out, okay, why do we need this, right? Like, how does this work, right? And it comes down to more tricks, right? Like the first one is when ChatGPT 3.5 came out, right? Like it had a memory all the way until I think 2021 or something like that, right? Where if you ask it like a question that was like, who's the like the president of Colombia on 2023 or 2024, it wouldn't know what to do, right? Like it would say like, look, I never learned that, or it was not of my training corpus, so I have no idea who it is, right? So this is the interesting part where there's a couple of concepts that come in. First one is is a lot of these LLMs have this concept of context, right? Where there is essentially, and we kind of have used that, like, sometimes you say like, look, using this information, and you put in a document or a poem or whatever it is that you try to work with. I want you then to do something with it, like summarize it, or make it prettier or something like that, right? Now, the whole text box where you wrote all that stuff and the document, that's usually called the context. And the very first, like LLMs has a very thin context, but they have been getting bigger and bigger, and now you can do a lot of like that text box essentially becomes very huge in terms of what it kind of remembers, right? Right now, I think in ChatGPT, it will keep a running, like if you have a conversation, it will keep a running list of everything that you have typed in, because it kind of remembers the previous instructions, and that becomes like the huge context. There's a point in time where it starts dropping off, when it doesn't know like the very first thing you said, and it scarily works like people. Like if I'm talking to Bob for like 3 hours, he would not remember why I did start talking 3 hours ago. But it's almost the same thing where having that context can guide essentially the weights on the neural network to get the right answer, right? And so one of the tricks that for example, um, uh, that ChatGPT start doing is, let's kind of use that context for bringing in new information, right? Like, and if you like, for example, the best one is like Perplexity AI uses this very well, where you ask the question, "Who is the president of Colombia now?" It kind of like splits up the problem in two. The first one is, it's like, okay, I realize that I don't know this. Let me go to the web and try to find out what the web says, right? And it does kind of like a search on the web, and then brings up some documents, and then kind of like plugged it in as part of the context, right? And then says like, look, I found this on the web. I want you to see if you can use this web information to kind of like um, answer the question, right? So the advantage is then now, the LLM doesn't have to be trained on past data, but it kind of like uses trick of retrieving some documents, putting it in the context, and then asking questions about that context to see if you can answer that. And I think that is kind of like using that trick is where embeddings and vectors
Yeah.
come to light.
You're getting into retrieval augmented generation, right?
Yeah.
So what a lot of folks call RAG. And basically you're taking some ability to search to create that context that eventually you're going to give a question to say, all right, here is the prompt I'm going to send. That prompt has information, and we're going to send that and create an embedding off of that, right? So we're going to get a vector of my prompt, and that prompt is probably going to have some keywords and some things about it that I could send back into a vector store in order to say, well, within your prompt, there's some things that you're asking about. I'm going to find text that is similar to that so that I can bring that information together and use that to build that context that you are talking about, right? So I'm going to retrieve information, build the context, feed in the context, and then my question. So then, as you mentioned, the LLM can use both its model as well as the context, which may include more recent and specific information to the question you asked in order to give you a better answer.
Yeah, no, and that trick is, again, it's one of those things when people were talking about rag this, rag that, and once you start looking at, oh, I copy and paste the thing in my prompt and then ask the question, that is essentially what it's doing. But it goes a long way, and this is also like the way that you will deal with, like if you have data that is really like very unique to what you're doing, right? Like it's part of your kind of company or part of your process, part of your, like the things that nobody will train an LLM on, right? Because this is unique to you. This is kind of like one of the tricks that you use, which is using the prompt. You first create the vector, the embeddings, like you said, and before that, you have a vector database that, for example, has all the documents that you use for, let's say, like an FAQ and things like that, or maybe there's policy in there, right? And then using these vector embeddings, and then asking the vector database to retrieve, give me all the policies that are related, for example, to this kind of travel, right? Like you're saying, like, I want to do a business travel, can I stay overnight, for $300 or whatever it is, right? The way that then that works is, yeah, like, trace embeddings, as the vector database to give me all documents that have, a concept of travel policies and all that, and then kind of drops it in the context, and then asks the LLM, use this context to answer this question, right? And again, a little thing, it goes a super long way in doing that.
Yeah, and frequently you're also having to combine that in different ways. So I mean, when you're creating an embedding, you generally want it to be a small and very specific thing. So when there's an entire process to this, where if you have a long document, let's use your example where you have policies, you're actually going to want to break up that document into chunks, right, of smaller pieces to generate embeddings off of not the entire document, because the entire document probably covers a broad range of topics, but small pieces of it. So you may get the section of policies on, when checkout times are, whether they allow dogs, whether they have parking available. So you would chunk the document in order to get those very small, specific policy sentences in their own embedding. And then you would match the prompt, because in your prompt, you may be asking about animals.
Can I bring my dog?
So you're much more likely to match on that smaller piece of information that was just talking about dogs in your embedding, rather than the entire document. But you run into a problem that if you only chunked that part of it, and all you did was retrieve what you generated the embedding with, you may miss some context about it. Like, so, yes, dogs are not allowed, but then maybe there's another chunk of the document that says, well, unless you need a service animal, then it's okay. So in general, when you get a match on a chunk, you're also going to reference back to the entire policy, or that context you're going to want is going to be bigger, that you're going to feed into the LLM to help answer your question. And this is conceptually called like the small to big pattern. So you use the small chunk embeddings to go back to the big document. One of my coworkers, Alex Ether, wrote a blog post on our company site kind of about this technique. But like, it's not there. There's a lot to this process of kind of going through and figuring out, okay, well, how do I break down the chunks into the right size? Where do I actually break? Is it at a paragraph level? Is it the sentence level? Should I just take arbitrary numbers of things, 1,000 words, 1,000 characters? Like, there's a lot of different strategies to this to try to find the right size in order to get good results from this process.
Yeah, no, and because, like, yeah, like, the embeddings return one vector. It's not just gonna return a sea of vectors. So
yeah,
the more,
well, no, usually you'll get similarity, and you'll tell it like, hey, give me the top 5. So but it's usually a small. To your point, you're usually not looking for 100 results. Like, that's bad, because then your context is going to get blown out. The amount of tokens you're going to be feeding to the model, it's going to be expensive. Like, there's a lot of things that happen when you try to add too much context to your search or to your prompt.
yeah, and so yeah, and that's kind of like what again, what you're trying to figure out. The other interesting part is that the vector embeddings are very related to the LLM that is going to either produce or consume. Like, if you're using ChatGPT 4.5 and you ask it to give you a vector embedding, that embedding is for ChatGPT 4.5. Like, you cannot kind of like cross embed, like, oh, I want to train or I want to create embeddings for my Phi 3, but I want to use it on ChatGPT, because the buckets that they're interested in are not the same. So they don't kind of like cross pollinate, right? Like that's, I learned
Yeah,
that.
it's more about the retrieval, right? So when I create my embedding, I want to create with the same vector that I'm going to use for the retrieval function.
Mhm.
Once I retrieve it and I get the actual full document, I could feed it into whatever LLM I want, right?
As part of the
So as
context.
far as the prompt part is concerned, but yeah, it's super critical for the what is creating the embedding and what is retrieving the embedding
To be the same.
to be the same one, because of the exact thing that you have on the screen right now. The output of these LLMs, so that the neurons that are firing as output, they mean a specific thing. And if you get a different model, that vector in position 0 is going to mean something different. So they don't align. They may also have different dimensions, right? So the models may have 768 dimensions. They may have, over 1200 dimensions. And that's the size of that output vector that you're encoding that embedding with. That also needs to match. So you have to use the same model to generate an embedding of the same size that you're trying to compare against.
Hmm. And like it's interesting because one of the things that I've been like looking into is essentially the small LLMs, right? The ones that you can actually run in your
Locally.
locally. Like you don't have to share your secrets with ChatGPT or anything like those, or pay per token, right?
Yeah. Yeah.
These are models that are able to be stood up in if you have just a decent computer, you can run it. And that's kind of like where the research is going. Like they're pushing very hard because they're like, oh, maybe we can create an LLM that can run inside the phone that
Yeah.
doesn't require going out. And those are kind of like the part, right? Like ChatGPT was, let me train it on the biggest hardware, the biggest thing, the biggest corpus, and produce the biggest LLM, right? Now that was done, now they're trying to say, like, how small can we get and still be effective,
Yeah, I
right?
mean, so a lot of the AI kind of started on vision models where they were much smaller models. They did one specific purpose. They weren't really general purpose. And now a lot of those models are the same things that you see in cars that are doing like collision detection things, where they're or distance away from vehicles as they're being fed into these very fast forward feed neural networks that can make decisions and classify things in fractions of a second. Right now, these LLMs, like the ones that are running on big iron with 1.7 trillion parameters, those don't work too well on your laptop. The models take up a ton of space. They are not fast unless they're all in memory. So a lot of what you're seeing is you do see a lot of these companies releasing smaller versions of the models with, say, 7 billion parameters. So like Facebook's Llama 3 has like a 7 billion parameter model that takes up 4 gigs of memory. So it's not, or 4 gigs of, it's a 4 gig model that you can download. Um, Takes up, okay, so there's an 8 billion parameter. Sorry, I misspoke. They have bigger ones, but if you're going to try to run it on your laptop,
Mhm.
strongly suggest like something in the 7 to 8 billion parameter range, unless you got a whole bunch of hardware and maybe some GPUs. Um, but in that 8 billion, 3 billion space, like, yeah, it's going to be a couple gigs, but you can download it and you can run it. And I see you've got Olama up, which, is wonderful because it's an open source project that abstracts all of that lower level stuff away so that you have almost like an open AI chat completion REST interface to work with, where it's like, here's my model, here's my system, my user prompt, here are some of my hyperparameters that I'm going to put in on how I want to tune the model. Give me a result. And then I can swap out using Llama, Mistral, all the different kind of hot models that folks are using against a common interface. So very cool project. Um, again, the REST API, like I've been actually messing around with it quite a bit at my new job, just because, like, to your point, Freddie, it's there's going to be a lot of companies out there that don't want the data going out of their firewall. So how can I bring these kind of smarts inbound and do things with them? There's a lot of these models are very text based, so they're very much big on the chat completion. There are a few visual models, like the Lava model. We'll take images and describe, what's in images, and it can do, so yeah, the Lava model there. That one has vision support, so you can feed it base 64 encoded images and ask it questions about what's in the image. Not all of the models have vision. In fact, most of them don't. But yeah, you've got a lot of different options to play around with, and they're very hot swappable, which to me was a lot of fun. I mean, again, like even like downloading the model, it's an API call, so you can orchestrate a ton of this stuff to just work.
Yeah, that's one of the things that is kind of nice, like because you install essentially you install the Olama, and the Olama will be like it gets me a little bit of the bias of Docker, but without being as heavy-handed as Docker, where you have an agent running and you can just call it, like download this. I've been my favorite to play with is 5.3 because it's it runs very, very quickly
Mm.
on my hardware, right? Like, and it does
Yeah.
have some hardware acceleration if you happen to have like a GPU, and kind of like a sidetrack note. Like if you've been following the LLM news, um there has been like Nvidia is considered the king of hardware right now, and the reason why it's now that you're getting to see is that neural networks, they are very GPU friendly, and vector spaces are also very GPU friendly, right? Like these kind of technologies, like GPUs, are very massive parallelizable tasks that are not like they are not interdependent, and they kind of like go into like you kind of like roll the drum, and it's like one second iteration, third iteration, and they can do like I think like multi-million cells in them that they can do the computations that are interdependent, and that's kind of like the reason why like a lot of like what is it? I think OpenAI wanted to buy all the NVIDIA GPUs that there was for the next 20 years, and I think valuation $1 trillion or something crazy like
Yeah. I mean, it's graphic cards, it's really all about mechanical sympathy, because, graphics cards are good at LLMs because of the same reason they're good at graphics. Most of what you're trying to do in graphics is a bunch of concurrent vector arithmetic. So you have
yes.
hardware that was built to specifically do that for video games, where you have concurrent things changing and moving around, and you're calculating, if how light hits something, how does it reflect, how does it look, and you're trying to do it all concurrently, so it's fast enough that the human eye doesn't perceive that it's fake. LLM, it's the same thing. You have vectors that are being manipulated in parallel, being pushed through, and that hardware is very, very efficient at doing those calculations in a massively parallel scale, so you get your result much faster than you would with a CPU in almost all cases.
Yeah.
So yeah, I mean, you'll see that most of these libraries and the model runtimes, they do have some complexity to them in order to support the GPUs. When you're flipping out chip architecture, guess what? The compilation changes. There's different libraries that are pulled in. So for NVIDIA, CUDA is I hope I'm saying that right. That's what I've been calling it, is CUDA,
Yeah.
is the library that helps you leverage that hardware behind the scenes. So if you're trying to use any of this stuff on GPU, you've got to make sure, especially like if you're using Docker images, make sure you're getting the image with those libraries pre-installed. And when you're starting Docker, make sure that to enable the GPU support so that you're getting that GPU running in the container.
I wonder how many times that has that happened.
Oh, I think it may have happened today. So, um, so I mean, it's really important stuff to operationalize. Again, your LLM and your AI within your company is to have a good understanding of the hardware that goes behind it.
Mhm.
But yeah, I mean, there's a lot of other things. There's various runtimes. There's you look at the fun thing about Olama is it turns it all into REST calls, so it becomes very language agnostic. If you're a Java developer and you're trying to get into this, using Olama as an interface in order to try out different models is probably going to get you going a lot faster than going to Hugging Face and learning Python. Now, I mean, for my job, I am writing a good amount of Python as well, because that is where a lot of the model development and training is happening. You look at the tools like TensorFlow and PyTorch, those are entire Python libraries that are used to train, to architect the network structures of all these models and then produce a serialized format. Now, the good thing is there's a lot of serialized formats out there. And one of them I've been playing around with a lot is Onyx, that I actually wrote a blog post on recently. And Onyx is a more language agnostic runtime. So, if you're a Java developer and you're able to convert your model to Onyx, you can actually run it on the JVM and feed your vector of floats directly into that model and get your results in Java floats coming out and work with those results directly within the JVM without a Python runtime running in the background, which is, can be very attractive to a Java developer, primarily Java developer like myself.
Aha. No, and I think that's kind of like the fun part that we have is I think that there is now a growing Java AI community, right? Um, and there are tools that are coming up. Like the one that I personally use to like try both, for work and for play is Spring AI, right? And this is super easy. The advantage is that Spring AI is a very Spring style where you do the includes, you put in some annotations about what model you want to like bootstrap into, and some configuration about how to access that model, and then you're off to the races running, right? Like one of the things that I do like is, for example, it has support for all these, but it actually has support for Olama, right? And it's super easy. You have essentially the Olama agent running locally. Spring AI just ask, where's the agent located? If it's the default HTTP localhost 2712, I don't remember what the port is, then suddenly, it discovers that, and then it's a matter of just plugging in however you want to, what is your controller, what is your what prompt you wanted to send, and suddenly you have a Java, bound control of calling the element, receiving the responses, having the context, and all that good stuff. So super easy to get started. I think we're gonna put the links in there for people to go in. One thing that is interesting that is worth discussing, just so people don't get too lost. Every one of these models have almost like a description of how their prompt is structured, right? So, for example, if you go to Phi 3, let's see, here in the parameters, this is kind of like the way that they structure the prompt. Each model, because it has been trained in a very specific way, will have different ways to actually uh, um, prompted for responses, right? You can just send plain text, but once you start trying to do things like the RAG, or you're trying to do things like LLM agents, which is again another huge discussion we can have. you want to understand how the model uh, gets its input or how it was trained. Oh wow, they have an Onyx.
Oh, there you go. But it's so, but if you look at the Olama API spec, I believe most of, um, if you're going over REST, and I don't know if those parameters are talking about something different than REST, they are basically using the system prompts of, hey, here's the user, here's the system, here's the assistant, and there's a common API for all of the chat completion, regardless of which model you're using.
Ah,
So I think the really important thing to point out on this screen is the license. So as much as it's wonderful to get your stuff working locally, you kind of got to pay attention to these licenses if you're going to start talking to your boss about pushing it to production, because some of these licenses have a lot of terms in there, that are not necessarily, how most of us understand open source. The models are fine to use, they're fine to mess around with, but once you start commercializing them, a lot of these licenses have restrictions based on the size of your company. You're kind of signing that, hey, I'm not going to use them for evil clauses, which, not necessarily a bad thing, but who's arbitrating what is good and what is evil in these cases? Lawyers from Microsoft, maybe, or Google. um,
yes.
so it's very important, even though, hey, we've got a bunch of open source surrounding it, we've got all of these models packaged together, and we can hot swap them in and out. Read the license, make sure you're able to use it, because if you start using this stuff and you're not supposed to be using it, I think we all know those are not fun conversations to have with your corporate lawyers or other companies' corporate lawyers.
See, you can copy and paste this into the context and just ask, "Can I use
Can
you?"
I use you? Yes. Will the model lie about its own usage? Yeah, great question. Have not tried that yet.
That would be a fun one to
But
try.
yeah, it's probably more important that the human beings, the model's not in any risk of being sued. I've not yet heard of a court case where the model got sued and you
in
got
in, in
paid out.
Boston court, right, right.
The
And
companies.
one thing though that I think that the last part of closing is it knowing, actually it's kind of a little bit related to this, is the concept of hallucinations, right? Um, Now that you essentially pulled the curtain back and saw that this is just trying to predict what the next word is, there's nothing more or nothing less about it. Hallucinations start making sense because essentially
Well,
it,
explain what a hallucination is first, Freddie.
I guess it's like when you ask a question or you're prompting something to the LLM and it comes back with a very, like, sometimes, well, actually sometimes it doesn't read well, but like something that it looks super like, convincing, that is completely wrong or is completely made up or really just doesn't exist, right? I think like, and there's like 100,000 examples of in the web already about like people asking it, like, remove the letter I from some word that didn't have an I, and it's like, hey, I remove it, here it is, and this is how you look at it. And the reason why like, these kind of like, gaps happen is because, based on the corpus that the element was trained, again, because it's just trying to predict the next word or token, sometimes it just does not, like, it's just predicted the wrong token. And there is it's interesting too, because there are like, I think like the first LLMs were trained without any knowledge about numbers, right? So numbers usually
Mm.
use all the elements because for them it's just another token. So it did not like, it was hard for the LLMs to do math. I think now the new models that are being trained, they're being trained with almost like a different bucket, or almost like a different way of processing what it realizes are numbers. But to be honest, like that is a real thing, right? Like it because it's predicting the next token. there is, there's always the risk and danger of an LLM
Yeah.
just producing.
Coming up with an answer. I mean, it's the analogy I like to use, because the LM is always going to try to give you an answer. It doesn't like to say I don't know. Right. So it's kind of like when you're in a Java interview, and the interview, like, you're kind of getting a vibe that you're talking to somebody that's not really a Java developer, but they read a lot of Java blog posts and they're giving you answers to your questions that sound really good, but it's like, I know these are wrong. That's kind of how I use the hallucination is you can't, it doesn't want to say I don't know, so it just says the best thing that come to mind, and a lot of times it sounds really good. So they call it a hallucination, but really it's just bullshit.
What was it like? There was that novel that had the gosh, it wasn't Seven Eves. It's Neil Stevenson had this novel where they had like actually like a tower of monks, and they actually have like a real hard definition of bullshit. Like it's, like it's like this is what it, and it kind of reminds me of that. Like, yeah, it's just plain wrong. um but the kind of like asterisk that we put with it is that, if you happen to hook this up in production, you gotta be very careful. I think that one of them was the latest example I know, it was Southwest had a chat agent, and somebody was asking, it's like, can I get a refund for this ticket that I bought here? And the chatbot said, yeah, of course you can get a refund. And suddenly, when you actually look at the rules and regulations, there was like, it was a basic economy ticket, you couldn't refund anything, it was already spent. But they took it to court, and the court said your chatbot said that it could, so they should honor that. So like that is, so that is kind of like the real risk of hallucinations. And
Yeah.
kind of like they're like, somebody did ask me like, what is this career that I hear about, prompt engineering? And it's I tell, it's like the fastest upward and fastest downward, popularity of a career that I've seen, right? But it does, but so what it does highlight is like there is some way to you to try to protect yourself by, for example, specifying the instructions in the prompt that if you really do not know the answer or are not 100% sure or whatever it is, say I don't know. Like there are ways to like kind of like coach the prompt to try not to give things away, and that's kind of like what they call guardrails on the stuff that you that sometimes it becomes even like a loop of a loop, like where you get the response, you feed it back into it, is this something that I can say? And then kind of like you build this kind of like a tower of, you first ask the question to the element, you get a response, then you ask it again just to make sure, are you sure this is right? And then sometimes the LML will say, I'm not sure, and then you can kind of like correct in there. But all of these are tricks, because at the end of the day, elements do not have, they cannot think. It's not like they're alive. It's just they're just really trying to predict the next word. All right. And with that final asterisk, I think we're done. Now you're an LLM expert, right?
Well, you have some of the fundamentals, like, so again, I mean, it's a huge space. It's constantly evolving. I think we're just talking about kind of the first iteration of a lot of these patterns that are coming out in order to deal with, how do you retrieve information, how do you establish context, how do you use them. But I mean, I see this is going to continue to grow. There's going to be more and more different, you know, techniques and things coming out of it. And as a Java developer, it's doing what you've always done. It's trying to figure out, okay, well, how do I integrate this into something that is already running in my enterprise? Pull out the good bits, the things that I need, and try to not do it in a way where I'm going to risk the business. So, um, I think learning about how they work, learning about which models and which licenses and which run times and all of that is going to be a critical skill set. So important to listen to this episode, and I'm sure we're going to talk more about these things too as they continue to evolve, and maybe what we really need is a deep dive into some of these systems and how they work now that we've got the fundamentals down.
Yeah, I think so too. Like, I think this is something that is going to stay with us for a little while. And I don't think like any of this is going anywhere. Like, it's, if anything, it's just we're gonna keep building up from where we are. So yeah, we'll do more as they come out, right? So it's gonna be fun.
Absolutely.
And with that, that's all what we have for you today. Well, keep listening, give us a like, and happy programming. This is Freddie signing off.
Bob signing off.
All right. We did it.
We did it. All right. I'm going to